Questions about anything at all before we get started here? Things are okay? All right. So today we're going to talk about probably, arguably, the most important distribution, especially in statistics, and that's the normal distribution. My goodness, I don't know what that problem. So that's what section 3.3 talks about. All right, so before we define what the normal distribution is for a couple of arbitrary parameters, let's talk about a specific integral that we actually need to be able to compute, or at least approximate, to be able to do probabilities associated with the normal distribution. So let's just first consider the function f of x equals e to the negative x squared. Whether or not x goes to positive infinity or x goes to negative infinity, your exponent here is going to go to negative infinity. So this is going to go to 0. At both your tails, both on the left and the right. And the highest this ever gets would be a 1. Now this is going to get adjusted later on for other distribution or other normal distributions. But it's also symmetric about the y-axis. It's got a high point on the y-axis. Since it's symmetric, what can I say about the area to the left relative to the area on the right? To be equal, right? And since it's nice and symmetric, and we've got that point there, the mean, it would also, well, when we get to that point, the mean will also be right here in the middle, and the high point is in the middle. So we talked on your last assignment, I talked about finding the mode was the high point of your distribution. So for a normal distribution, one of the characteristics is that the mean, the median, and the mode are all equal to each other. Okay. This is not a normal distribution because the area under this won't be 1. But we'll have to adjust it to make the area 1, and we'll talk about how we do that here in a minute. But let's talk about how we would actually compute this integral. So if I wanted the area under the curve, you would have to do the integral from negative infinity to infinity of e to the negative x squared dx, right? Well, e to the x squared, or e to the minus x squared, is one of those functions that you cannot write down the antiderivative for. Technically, what I mean is, when I say that, I mean that you cannot write it down in what's referred to as closed form. If I use power series, I can anti-differentiate e to the negative x squared, but it'll be a power series. Okay. But if I want to just try to write it down, I can't write down an antiderivative, because here I would probably want to use a u substitution, but I don't have a 2x. Right? So that's why I can't anti-differentiate it. There are a whole bunch of functions that are both useful and not integrable as I shouldn't say integrable, not anti-differentiatable. E to the x squared is one of those. Sine of x squared or cosine of x squared is another one of those. Square root of 1 plus x cubed is another one of those. There's a whole bunch of functions that you can't just do an antiderivative of, which makes using the fundamental theorem of calculus hard. Okay. So that's why in Calc 2 and in a numerical analysis class, you spend time talking about how you approximate integrals rather than actually compute them by hand, because many integrals that you come across, you can't actually do by hand. All right. So anyway, let's talk about how we actually approach this. So I'm going to refer to this area as it. Your book does it too. I'm going to call it I. It's just what's stuck. I think it's I for integral. Okay. If I square this, then basically I just take the integral and multiply it by itself, right? Now don't bother filling in a variable on the second one yet, because I'm going to erase it in just a second. So don't write the don't write the variable in the second one. Does this variable matter as far as this integral goes, or vice versa? No. So I can call this a different letter, right? Okay. So instead of calling it an x, let's call it a y, and I get the same thing. Okay. Now, assuming that these integrals actually converge, and if you remember doing comparison test things back in Calc 2, I can show that these integrals actually exist. In particular, they're below 1 over x squared, and 1 over x squared definitely converges. So I can show that each of these converge, but the reason why I mention that is, that means they're both constants, right? Well, if this is a constant, I can pull it inside that integral, correct? And then as far as this integral is concerned, that x is a constant, so I can take that e to the negative x squared and move it inside here. So we can rewrite this thing as an iterated integral. And you should remember iterated integrals from Calc 2 and Calc 3. I can rewrite this as an iterated integral in this fashion. One of the reasons why I wanted to talk about this, besides the point that I think this is a cool way to get at what the answer has to be, we're going to do double integrals in the next chapter. So I wanted to remind ourselves of what an iterated integral looks like. So again, the process here is take this constant, pull it inside this integral. Then e to the minus x squared is constant relative to this integral because the x is not a y. So I can pull it inside that integral, and then I just combine my exponents. Okay. Now looking at this iterated integral, I notice I have an x squared plus y squared here. Right? When you see an x squared plus y squared inside of an iterated integral or inside of a double integral, what does that make you think of? Yeah, r squared. Makes you think of polar, doesn't it? So if I convert this to polar, I'll worry about the bounds here in a second. We'll get an e to the negative r squared, because x squared plus y squared is r squared in polar. Right? I'm glad you got that out of Calc 2 or Calc 3, because that's one of the right thing to think about. If you see an x squared plus a y squared, you think r squared immediately. It's great. What happens now when you replace the dy dx? What do you get? R dr d theta. Wonderful. Now remember what I said? This integral up here we couldn't do because what was missing? Yeah, the x, right? For a 2x, for a u substitution. Look what popped up. That thing I need for the u substitution, right? Now I have to worry about the limits. Okay, so this negative infinity to infinity in both directions describes the entire plane, right? It's the whole plane. Negative infinity to infinity for x and for y. I want to change these to r's and thetas. Well, if I do x squared plus y squared, your r just goes from 0 to infinity, doesn't it? What does your theta go to? 0 to 2 pi, because it's the rotation, right? It just rotates around. That's not improper anymore. Whoa, hey, that went flying. That's just 0 to 2 pi. All right, first, before we go through all of this, any thetas in my integral? So what does integral from 0 to 2 pi do, practically? Just multiplies by 2 pi, right? Good. So I have a 2 pi. Antiderivative for r, e to the negative r squared. If you let your u equal negative r squared, your d will be negative 2r. So I need to adjust with a negative 1/2. And it'll be e to the minus r squared, evaluated from 0 to infinity. Okay? Okay. So now you put in infinity, you'll get 0. You put in 0, you get 1, right? somewhere along, oh, yeah, that's fine. All right, so when you put in a 0, you get a 1. We end up with 2 pi times just a 1/2, don't we? Can we get pi? Oh, we're done. So going back up to the original then, what did we do to start? We squared, didn't we? So that means that this was must be equal to square root of pi. This is pretty cool. Notice that's the second time we've come across square root of pi, by the way. That was also gamma of a half. Yes.
As you say square, when did you put a square?
I have to undo my squaring to get back to the original. I squared to start the problem, so I have to undo the squaring. Right? I squared the integral to start, so I had to undo it to figure out what the value was to start with. Okay, so this integral is used, and like I said, I did this mainly because I like it, but I come out of that thing, right? Got an E and an X, and you got a pi that popped out. That's just weird. At least I think it's weird. I think it's cool, but I think it's weird. In any event. All right. So where does this come up with your normal distribution? All right. So again, with a normal distribution, we're going to want things to come out to 1 versus a 2 pi, excuse me, a square root of pi or something along those lines. So here is actually your definition for the normal distribution PDF. All right, so out in front, you're going to get a 1 over square root of 2 pi sigma squared. What's sigma squared again? Usually, we usually use that for the variance, right? So we get that's actually going to turn out to be the variance for this thing, and then it'll be e to the negative. It'll be x minus mu squared over 2 sigma squared. I know it looks ugly. What have we done to that original function? Basically, we've done some transformations, right? This sigma squared piece is going to do a horizontal stretch or shift. Or excuse me, not a horizontal stretch or shift, it's horizontal stretch or compression, right? Depending on what the theta or the sigma is, right? It'll either make it really, really wide or really, really narrow, right? Remember what's done on the inside of the function kind of reverses what you think it should. So if you take a number bigger than 1, it'll stretch it, it'll compress it. If you take a number less than 1, it'll stretch it, right? Well, we want to think about bigger variances giving us more stretched out different distributions, right? That's why we're dividing by the variance in there, stretching things out, okay? What does subtraction do? It's a shift, right? So this is going to move, basically what this does is it moves your high point, and we already talked about the high point being the mean. So that mu is representing the mean, which is why we use the mu there. Okay. This number up in front, well, I did some transformations, right? I put a 2 in the denominator, and I put a sigma squared in there. Remember, this integral turned out to be a root pi. If I put the over 2 in here, I would have got a root 2 pi. So I need to make sure that goes away because I wanted to integrate to 1, right? Not square root of pi. So that's adjusting for the constant out in front. And this is doing the same thing to adjust for that sigma squared that's in there. Okay. This is the PDF for the normal distribution. The mean is mu, and your variance, of course, is sigma squared. We will talk about why this particular function, this particular distribution is important at the end of the semester here. But if you've done any statistics, you've played with normal distribution before. And we'll also talk about today the importance of why I said the chi-squared was important as well. We'll see why that's important. Yes.
How much the line?
The mu is not squared, it's x minus mu quantity squared.
Formula for finding the variance. Maybe this one.
The formula for finding the variance of a distribution, it would be expected value of x minus mu squared. Yeah, it's expected value of that. All right. For moment generating function here, you get, I don't remember what it is off the top of my head. It's e to the mu t plus sigma squared t squared over 2. You'll notice in your book, they'll write this as exp of this, like so. If you've used the exponential function in Excel, that's kind of the same idea, right? It just means the input is your exponent. It makes it a little bit easier to read if you do it that way. Okay. Just remember that this really is an exponent for the e. If you see it this way, I'll usually write it this way because I don't particularly like this notation, but know that it's in your text. Okay. All right. In any event, that is our normal distribution PDF. You can check that it's a PDF by basically doing the appropriate substitutions to get to here. Okay. Basically, you just make a substitution. If you would just take your squared out and do the appropriate substitution to make that a u squared up there, and then your constants will all adjust accordingly. Which is why I'm not going through it. All right. You can also they go through how to get the moment generating function, and they use that to show that the mean really is mu and sigma squared. And again, you can go in the book if you're really super interested in that. It's not particularly interesting, which is why I'm not doing it. Or at least I don't personally find it interesting. You may enjoy it. Okay. All right. Let's talk about how we use this thing. Well, if you've done any statistics at all, you've probably used the normal distribution table, which I forgot to print off today. I'm an idiot. That's okay. You've probably used the normal distribution table. The normal distribution table is for one specific normal distribution, right? One specific thing, right? So that specific normal distribution is referred to as the standard normal distribution. Standard normal distribution means that your mean is 0 and your variance is 1. Okay. Basically, it's scaling it to one specific distribution. It's putting the high point right directly in the middle, and it's making whatever the stretch is, whatever the stretch is, smash back into place to make it a stretch of 1 rather than a stretch of whatever the heck the variance was to start with. Okay. So the whole point of when we do a standard normal distribution is that we're going to convert everything into the standard normal to be able to answer questions. Okay. So when we talk about how we convert to the standard normal distribution, by the way, I should mention that if you see the capital letter Z, that's typically going to denote the standard normal distribution. A general normal distribution will represent as an N, and then you always put the mean first, the mean first and the variance second, okay? So generally you'll see a mean of mu and a variance of sigma squared, and that'll be the two parameters that you have. Okay. So how do we convert a general normal distribution into a standard one? All right, well, let's look at our PMF again. This was our general PMF. That's our general PMF. If I want to convert this to the standard normal, well, what would be the standard normal? Well, that's going to be a 0, and that's going to be a 1, okay? You agree with that? That'll be a 0, that'll be a 1. So what we'll see in our standard normal distribution instead would be a 1 over root 2 pi times e to the minus x squared over 2, right? That's going to be the conversion. We got to go this way. All right. Well, notice that, and I mentioned this a minute ago, this piece right here, is like x minus mu over sigma, whole thing squared. And then there's an extra 2 out there, right? We agree with that? So the substitution you'll make, I'll call it, I should have wrote that as a z. I'll call it z equals x minus mu over sigma. That would be the substitution if I want to convert one to the other. Now think about it in terms of an integral. What would your dz be? If I were thinking about doing it as this is a substitution into an integral, your dz would be what?
Mu.
Not quite, because that would be a constant. The mu would be a constant. I agree there's an over sigma part, but it'll be 1 over sigma. Yeah, good. All right? It'll be a 1 over sigma for your substitution. Notice that I would have to adjust for this 1 over sigma, right? How do I adjust for the 1 over sigma? You'd put a sigma on top, but sigma is the same thing as square root of sigma squared, so that's where those cancel out. Okay? So it's this substitution that allows us to change. It's this substitution, change color, right here, that allows us to change from any normal distribution to a standard one. Okay? So that expression we typically refer to as a z-score. If you've done any statistics, you've probably computed z-scores, right? So this is called your z-score. Okay? And again, that transformation allows us to change from any normal distribution to a standard one, which allows us to go to a single table to compute. Or you can use your calculator. Or you can use Excel, of course. Or pretty much any program anymore has statistical functions built into it. You can usually use those to calculate probabilities. All right, so let's see if we can start working on some problems. All right, so let's scroll back up here. First example I have in here, and like I said, I totally forgot about printing off the table today, but I do have it on the screen, so I'll show you here in a second. This really is just an exercise in how do you use the normal distribution table that is given to you in your textbook, okay? That's literally what this is how do you use a standard normal distribution table? So let me flip over to that real quick. And I have the problems here since not everybody's here. Here's the standard normal distribution, okay? All right, so the first thing I notice about the table before I get to the numbers, first thing I notice is that right here, they've defined the area in terms of the cumulative distribution function, right? Remember, your definition of your cumulative distribution function is accumulated probability up until a certain point. In this case, that's a function defined as an integral, right? I would integrate from minus infinity up to that point, the standard normal distribution function. Right? Okay. So notice that a lot of times when we're trying to use the table, we can phrase the questions like we did with the exponential distribution because we have the CDF for the exponential distribution, right? Accumulate up to a certain point, and then if you need to, subtract off. This part right here is using the symmetry of our distribution. It notices that if you go the cumulative probability to the left of a negative, well, that probability there from symmetry would be above the positive, and I can calculate that by doing a complement. That's what that part's saying. Okay, we'll practice with these, so I'm not expecting you to get all this just by me saying it. I'm just telling you what those pieces are. Okay. But using these properties, that's why our table just starts at 0. We don't need to worry about the negatives because we can compute the negatives using that complement. So that first question was asking that it asked you was the probability that z is between 0 and 0.87. Okay. Using the capital letter phi, how could I express this as a difference of cumulative distribution functions? If we're using phi, phi or phi, whichever way you want to call it. Good. That's how we would do it as cumulative distribution functions. Again, you said f, which is fine. But we use the Greek letter phi for phi. Doesn't matter. When I learned stuff, the professor said phi. That's why I say phi. If you want to say phi, I'm fine with that. Okay. Phi, phi, pho, phone, doesn't matter. Okay. Yeah, exactly the same. It's just the CDF. It's just a different name. Yep. All right. So that would be in terms of the CDF, and that's what we're going to be gunning for, hopefully, in all of these problems, is so that we can go and use the table. Or again, you can use your calculator. I'll show you what the Excel commands look like in a little bit. First, let's just look at the phi of 0. That one, you don't even need a table, right? For the standard normal distribution, the y-axis cuts the distribution right directly in half. So what is phi of 0? It'd be 0.5, right? It cuts it right directly in half, okay? So I know I'm going to subtract off the 0.5 there without any question. I could also see that from the table, but it wasn't very interesting reading the table from that. So let's talk about how we read the table. If you've already seen this, you know how to read the table already. I want 0.87. So notice what we do is basically we break it into two pieces. The whole number and the first decimal place, and then the second decimal place, okay? So notice down your first column here, we've got whole number and first decimal place, right? And then across the top row, we've got second decimal place. So if I want 0.87, I'm going to go down to the 0.8 row and across to the 0.7 and get 8078. Oops. So again, that was right here. I apologize for not printing off the table. So far, so good. And then subtract 0.3078. Great. Let me flip over to Excel real quick and see if we can show how to do that on Excel. On your calculator, it's in the same place where we did the exponential, gamma, and all that stuff, binomial, geometric, all those PDFs that you had in your calculator. The normal CDF is in there as well, so you can do it on your calculator. All right, so let me show you normal distribution here. All right, so, pardon me, there's a couple of different ones in here. Norm.dist is your normal distribution where you would specify both what the mean of the distribution is and what the variance of the distribution is. It might actually be standard. Oh, no, it even says standard deviation. So you have to do the square root of variance. The norm.s.dist is your standard norm. So you don't have to do mean and variance there. It knows that mean is supposed to be 0 and variance is supposed to be 1. The .inv's do your percentiles. You would be given a probability. You figure out the x value that corresponds to that probability. Okay, that's what the INV does. Let's go down to the third one here. My goodness, sorry. Where we want to do the cumulative distribution up until that point. Our z value, that first one was 0.87, and then just like before, you'll make it a true. We did that with a gamma distribution, didn't we? And the chi-squared. Same concept, different function. There's that 0.8078. I didn't minus the 0.5, obviously, but that's how you would use Excel on these. Okay. Reason why I'm showing you this is not so much that I'm expecting you to do it in an exam, just that you should be have facility with Excel. So it's such an important computational tool. You should know how to use it, at least somewhat. Especially if you're going to go into any job in industry at all that involves computations, you better know how to use Excel. All right. Let's do the second one. So the second one was probability that you've got negative 0.64 less than z less than 0. Again, straightforward application of cumulative distribution function. How do we rewrite this?
Minus 5.
Good. That's literally just straightforward application of cumulative distribution function, right? Okay. Now, we already know that we do that phi of 0 is 0.5. You can also see that on the table, right? It's right there, isn't it? Okay. This one's not on the table because of that negative sign. So this is where we're going to use that other property. And let me just draw what the picture that I'm talking about here. So this is the probability we want, right? That's not in the table. Using the symmetry, that area is the same as the area above 2.64, right? We don't want what's above it, we want what's below it, so we want the complement, right? So this area, all of this area is 1 minus that, right? It's the complement of that. I just wrote it where I wanted it. Okay, so going back to this, we can rewrite this as 1 minus phi of 2.64. Okay. And now I can figure out the different pieces on the different pieces in the table. 2.64. So again, if I scroll back over, I go down to the 2.6 row, which is right there. And I can't see in my top, so I'm going to scroll down or squeeze a little bit. Almost, there it is. And I want to go over to the 0.04 column up there. So it's this number right here that I want, the 0.9959. That one. Wait, 4959 for that one? That part okay? Is it making sense how we're using the table? You may have done this differently if you've taken another stat class using a different type of normal distribution table. Some of those have the area between 0 and the number you're looking for given to you. I don't know how many people have done stats before, but sometimes you see a slightly different one. This one uses it in terms of the cumulative distribution function. Okay. What's the next one? Oops. Negative 2.13 less than or equal to z less than or equal to negative 0.56. Using cumulative distribution function, how would we rewrite it? Yep. Yep, exactly. Those numbers aren't in the table because they're negative, so how do I change them into numbers that are in the table? 1 minus each of them, good. Your ones will cancel, so I can write this as phi of 2.13 minus phi of 0.56. 2.13 is where did I lost it? 0.9834. That's this one right here. And 0.56, I know it's small. 0.7123. Doc will be on my evaluation at the end of the semester if you need to. I forgot the tables. He was not prepared for class ever. That okay? And what do we get there? 0.2711. I did my subtraction right. Questions on that? We okay with that? Let's look at one more. Doesn't really matter which one. Let's look at part D because I just want to do one with an absolute value. All right, so probably the absolute value of Z is greater than 1.39. Well, how does your absolute value get greater than 1.39? Good. And yeah, the important part was the or part, right? Either it's bigger than the 1.39 or less than the negative, right? Do these intervals overlap? No. So how can we rewrite the or statement? Because they don't overlap, it has to be one or the other. It would be and. Plus, there we go. Yeah, gonna add them, good. And then we can write them, well, almost in terms of the cumulative distribution function. The second one we certainly can, right? That one I can certainly do in terms of the cumulative distribution function. In terms of the CDF, how's the first one written? Good, good. Be 1 minus, all right? Because it's a greater than, so I need to do the complement. What's this one also going to be? 1 minus the same thing, right? So that's 2 times 1 minus phi of 1.39, because there's 2 of them now. And then you can go get that number in the table. Yes. What did I do it here? Is this in terms of the CDF right here? What do I have to do the CDF? I got to do the complement, right? Yep, I got to flip it. This okay? Are you comfortable with looking it up in the table, or do I need to go do that? Okay. All right. That's standard distribution and the table. So let's go. I'm probably not going to switch back and forth to the table. I'll let you fill out the numbers when we're done. Let's just see if we can get things set up in these other problems. So let's look at the next one. The point of this particular problem is to recognize what type of distribution you have from the moment generating function. Well, we're in the normal distribution chapter. section. So this is probably the moment generating function of a normal distribution, right? Okay. So remember, our moment generating function for a normal distribution is e to the mu t plus sigma squared t squared over 2, right? The thing to pay attention to, of course, is that it's that, right? It's sigma squared over 2 is the coefficient on the t squared, right? The mean we should be able to read right off. What is the mean? 166, good, right? Because that's the coefficient on the t. What about the sigma squared? It's 400, right? Because that coefficient is half the variance. Okay. Because sigma squared over 2 has to be the 200 here. Oh, I guess that was part B. They were both part A. That okay? So that was the point of part A and B. The other two parts are the point is to shift the general normal distribution to a standard one using that z-score idea. Do you have a question, Kevin? The coefficient on t squared is half the variance. So I have to double it to get the variance. Sigma squared over 2 equals 200. So I have to multiply both sides by 2. Okay. So I need to transform this to a standard one. And we talked about how to do that with the z-scores, right? So in part C, when I start with 170 is less than x is less than 200, the first thing we would do is transform it to a z. Oh, I put an equal sign. Do the equal signs matter, by the way? No. Continuous distribution again, right? So remember what we do to go from a general normal distribution to a standard normal. You take the x value, which in this case is the 170. You subtract off the mean, which in this case is 166. What do we divide by? Square root of the 400, right? It's a standard deviation, exactly right. Be careful with that. It's not dividing by the variance, it's dividing by the standard deviation, okay? In this case, your standard deviation is 20, square root of 400. Right? 200 minus 166 over 20, okay? Be careful with that. In a lot of problems, they will tell you, hey, you've got a normal distribution, 166, 400. It's easy to just to take the 400 and divide, okay? If it's written like this, that second number is the variance. So make sure you take the square root when you convert it, okay? So in this one, what do you get? 4 over 20 is the same thing as a fifth, so it's 0.2. And in the other one, did I do that right? Yeah, and the other one is 34 over 20, so you get 1.7. Assuming I did my arithmetic correctly. That's why you have calculators. And then now you can write it in terms of the CDF, right? And at this point, either use your normal distribution table or put your calculator or your Excel. I don't remember off the top of my head. I know the normal CDF is in there. I don't think the standard normal CDF is in there. I think you have to specify mean 0 and standard variance 1. Right.
It just says norm.
Does it just say normal? So I think you have to put the mean and standard deviation in there as well. Does it come up as a menu? Yeah. That's what I thought. But if you convert it to standard normal, then you can always just put 0 and 1 in there. You don't have to worry about it. Yes. Anytime that you have a normal distribution that's not mean 0 and standard deviation 1, you have to change it to standard normal. Yes. I know that because my mean was 166 and my variance was 400. Yeah. Okay. That one okay? I assume you're okay with me not finishing off the numbers? Okay. All right. Let's look at the next one. This one is kind of working backward. It's kind of doing those percentile ideas again, if you will. I don't need to do a lot of information to know the first answer. The problem's asking you for the standard deviation. Do I know the mean pretty easily? What is the mean? How do you know that's the mean? That's what splits the distribution in half, right? Remember, for a normal distribution, mean, median, and mode are the same. This is a statement about the median, isn't it? That's, if you had that for any distribution, normal or not, the median's 500. That's a statement about the median, isn't it? The median is what splits the distribution in half by probability, okay? Half is below, half is above. So this right here, again, does not matter what type of distribution you have. Doesn't matter if it's normal or not, you would be able to tell me right there the median is 500, okay? It just so happens in a normal distribution, the median is also the mean, okay? So this part right here is telling us that the mean is 500. All right, so let's ignore this for the time being. Don't cross it off on your paper. I'm just telling you to ignore it for the time being. And say you had probability that z being greater than something is 0.0227. Not worrying about what the x is why I crossed it out. What if I did it as standard normal? Do you have any thoughts about how you might attack that? Besides quitting and going to the next problem. Any ideas how you might attack that? First, is that a statement about the CDF? Let's go start there. Can I convert it to CDF? Yeah, this would say that 1 minus phi of something, I'll refer to it as a z, is 0.20227, or that phi of z is 0.9773. Yes. Hmm? No, this is just a statement about a complement. It's a greater than rather than a less than. The reason why I'm doing 1 minus is because I'm doing a complement. No. No, this is just a statement about a complement of a probability, right? Okay. Now thoughts about how you might use the table. What might you do? Keep that number in mind, 0.9773. What might you do for the table? Find it somewhere in there, right? Well, what's close? Yeah, 9772. That one's close, right? What z value corresponds to that then? 2, right? Because it's 2.00, right? So going back over here, from the table, we see z is 2-ish. Okay? Why did I do all of that? Good. That was z-score, right? Z equals x minus mu over sigma. What values do we know? I know the z is 2. I know the mean is 500. Now I'm going to go back up and erase what I crossed out. What's the x? The 650. That was the value for the x that we were interested in, right? I crossed it out and said ignore it, but really I was thinking I can do this in terms of a z-score. So my x is 650. My sigma is on bottom. We can solve for sigma. What does it get? 75? 150 divided by 2? Does that make sense? What's wrong with it? I said I'm not worried about this for the time being. I went and found the z-score, right? Going back now, I recognize I need the z-score of 650 to equal 2 to get this value. That's what I did. I need the z-score for this so that when I do the probability, I get this. That's how we're going to do probabilities for normal distributions. We're going to convert them all to z-scores. So I need the z-score for this to be that. So I had to figure out what the z-score was first. I don't know what you mean by the sign. Yeah, I didn't worry about the 650. I needed, because this is, instead of calling it something, I could have said z-score. That's what I wanted. Okay. And so then I'm using this to figure it out. Yeah, the equation. Okay. I just not equal to 650 necessarily. This is what the lower bound would be. So if you're looking at a picture, I'd be looking for this area, but I still need to know what this z-score is. I'm trying to correspond these two things together. That's what I'm trying to do, so that I can convert that to the picture that we have on the table. All right. This is more about trying to figure out what the problem's asking you. You've got your traveling time distribution given to you. And asks, if you leave by 8:25, what's the probability that you arrive to work by 9? So if X is your traveling time, what probability are you looking for? Good. So if we let our X be our commute to work in minutes, then we want that X to be less than 35. All right. So then we need to change this to a standard normal. How are we going to change it to standard normal? Good. Do our z-score. So we'll do what? With 75, right? And then I'll definitely need a calculator or Excel or something on here, right? Because I need a decimal. Square root of 35 is a little bit less than 6, so it should be a little bit better, bigger than 0.86-ish, so maybe 0.8889?
0.845.
Really? Oh, it's 833, not 866. Darn it. 0.8, what'd you say, 0.8445? If you're going to use the table, you'll have to round to 2 decimal places. So since it was 0.845, 5/6 is 0.833, not 6s. Dang it. Trying to get close. All right. So you'll round up to 0.85. And so then you'd look that up in your table. If you use a calculator or Excel, you should be able to just type that in directly. In particular, maybe I wanted to do this in Excel. If I go in Excel, I would do normal, standard normal distribution. I'll do it that way, or I'll show you how to use the regular one as well. The z-score in this case, I'll put parentheses, was 35 minus 30 divided by the square root of 35. The command for square root in Excel is sqrt. And then we want cumulative, so we should get that. It's about 0.8. So what you got on your calculator? Did you do it on your calculator, Trace?
What should I put for the lower bounds?
Ah, that's a great question. Wonderful. Yep, we'll talk about that here in a second. Let me do the other one real quick. You could have also not bought, if you're going to use Excel, you could use the regular old normal distribution where you would put in the X value, in this case was 35. That's the X they gave you. The mean is 30. You still have to do SQRT of 35 and then true. Okay. And get the same value. Better be. Good question. What do you put for your lower bound? So if you're going to use the normal CDF function on your calculator, it requires both a lower and an upper bound. If your lower bound is negative infinity, then you just got to put in a really, really large negative number. Put in like negative 1,000,000 or something. And you should get something that's close. So if your lower bound on your X value, or sorry, the lower bound on your integral that you're doing for your normal CDF on your calculator is negative infinity, just type in some large negative number. Sometimes you can just if you do scientific notation, you could like -1 times 10 to the 99th or something. It'll be fine with that. Yeah.
With a negative 1,000,000, 0.802.
So probably need to go a little bit farther then. Yeah. Yeah. Yes.
Why did you put, why do you put instead of that size no sign?
Because the number of minutes from 8:25 to 9 is 35.
It's nothing to do with it.
So it has nothing to do with the mean. No, that X value that you're interested in is 35. Yeah. All right, let's see what else we got here. So these problems are basically all the same. Let's look at the 23 point. Well, let's label 23.3. I think it's the next one past the next one. Thoughts on how you might attack it if the probability thing wasn't there? I just wrote down x squared minus 2x is less than or equal to 8.
So for
Yeah, right. You want to solve for the x part, right? So what I want to do first? Yeah, subtract the 8. That sounds like a good plan. What does that equal to 0?
X is -2, X is 4.
This is -2 and 4. Good. So I want to know when the product is negative. Now you could go through and analyze it by, well, I know I need one factor to be positive and one to be negative and try that out, right? See if we can think about it a little bit easier. If I were to graph this thing, what kind of a shape? Where is just to graph the left-hand side? What kind of shape? Parabola. Crosses the x-axis at 2 and 4. Does it open up or down? Up. What am I interested in? Where it is negative. So what do I need x to be for it to be negative? Good. Now, does that look like a normal distribution problem? Okay. Okay. So I'm interested in knowing when the product is less than 0. Well, that's the same as making sure that this is below the x-axis as a graph, right? You can think about it, right? I would need that x plus 2 is less than 0 and x minus 4 is greater than 0. Or x plus 2 is greater than 0 and x minus 4 is less than 0. The first case can't happen. X plus 2 can't be negative and x minus 4 be positive at the same time. That case can't happen. So you would need x plus 2 being positive and x minus 4 being negative between negative 2 and 4. You can analyze it that way if you'd rather think through it. I thought the graph was easier. Because I know it's a parabola that opens up. Right? Yep. Which part?
No, it's fine. I understood the first part.
The first part of what? You can wrap it okay? Oh. Was it the analysis of which one was which?
Yeah.
So, I'll go
No,
through
I
it.
got it now.
Yeah.
I'm good.
It's just when I multiply two numbers together to get a negative, one has to be positive, one has to be negative. The first case can't happen. That's what I was saying. I know I did it fast. You could do it that way. I just don't think that was the easy way to do it. You do it however you want. I don't care. You can also do it with, you've probably seen it in maybe a couple of different ways depending on when you learned college algebra or calculus, right? Sometimes you might see a sign chart made, right? And plug in some test points, you get a positive, a negative, and a positive, and we're looking for the negatives. Or you might have seen a table. The table is just the list form, right? Pick test points and do the same thing. And again, we're looking for negatives. My personal preference was that one because I was done 10 minutes ago. But now do you know how to finish this one off? Yes. Yep. So yeah, this is exactly how we're going to finish it off, right? So let's see if I can do it all at once. I'm going to have to subtract two cumulative distributions, right? If I want to write it in terms of the normal distribution, what would the first one look like? What would be inside the parentheses?
3 halves.
Okay, yep, so 4 minus 1 over 2. Yep, exactly right. 3 halves, that's exactly right. What would the other one be?
-2 minus.
Good. So you get phi of 3 halves minus phi of negative 3 halves, and finish it off from there. That 2 is coming from the square root of 4. And that one's coming from the square root of 4, yep. I have to do the z-score of both numbers. Why would I do square root of 2? No, we're doing the square. It's always the square root of the variance. It's always the standard deviation. Yeah. That's okay? All right. Just to mention what the last piece is, the next piece is here. These values that we list here come up in hypothesis testing. Again, if you have done any statistics at all, you've probably done some hypothesis testing where you look for rejection regions for sample values that you come up with. If you haven't done statistics before, you can ignore everything I just said. Okay? All right. So what these values are looking for here are basically, I'll call them tails, if you will, like we did for the chi-squared. So let me go back over to the table. At the bottom of the table, they've got these little z sub alphas at the bottom. The alpha piece that they're talking about here is the probability, the z value that gives you a certain tail probability. So what do I mean by that? So let's look at this 1.645 value here. Okay. What that 1.645 value means is that if I think about my normal distribution, and I've got my z value of 1.645, that subscript, that alpha, is telling me what is the probability here in the tail. That's what the alpha means. Okay? Why do we care? Again, I just want to tell you why we care about these things. We're not going to do them this semester. This is another statistics class, okay? But I'm just telling you why we care. If you think that your distribution of whatever it is supposed to be like this, and you come up with a value that lands over here, that seems to be pretty rare, right? That happens less than 5% of the time. That's what hypothesis testing is about, right? I think I have a certain scenario, I look at a sample, I calculate whatever values associated with that scenario, and then I see how likely that scenario happened given what I think is true. That's what hypothesis testing is all about. Okay? So that's what these values typically look for. Is they're called critical values in hypothesis testing. That's all it's asking you about. So the problem that you had was z sub 0.1, right? It's looking for, in the picture, your z sub 0.1, z sub 0.1, it says that the area here is 0.1, right? Well, if the area here, if I didn't have these listed at the bottom, if the area here is 0.1, what's the area that's not colored in? 0.9. So you would go back up to your table and look for 0.9 in your probabilities, or at least as close as you can get. That's in between those two values, right? 0.9 is in between those two things, right? This corresponds to 1.201234567 That's 1.29. It's closer than the 1.28 than it is the 1.29. That's why this value over here is 1.282. Okay. What if it asked you for z, the negative of z sub 0.05? Well, that's not too hard to figure out. That's going to be negative 1.645 because it says just do the opposite, right? And I boxed that in earlier. There's your z sub 0.05. Graphically, what does that represent? Well, the original was the 1.645 was over here, and I had 5% of your area was on that side. Graphically, what does this value represent?
Yeah,
95% on the right or 5% on the left, right? Why would I might be interested in that? Well, again, from a hypothesis perspective, I might want to say, well, I think this is my distribution, but my sample gave me a value that was lower, right? So I might want to know what's over on the left rather than on the right. That's why they're doing these negatives. I didn't say it was particularly interesting. I just said that's what these values are for. Okay. From our perspective, it's not particularly interesting because it doesn't really matter. All right. Let's see how we would figure out the other two. It says z. Well, we'll do the negative. I don't really care about the negative. Z.0485. Ignore the negative in front to start with. 0.0485. That's a right tail, right? Because the way I have it written without the negative, it's on the right. So I need to find 0.9515 in the table, right? Go find my 9515. Let me scroll up. There it is. Shockingly enough, they gave you one that was in the table. 0, 1, 2, 3, 4, 5, 6. So that must be 1.66. And then the problem asks for the negative, so you put the negative sign in front of it.
So you would both.
Not both. It was the problem asked for that, right? So it's going to be in front of both of them. The negative didn't matter for actually finding the value. Does that make sense?
You just done a negative.
The problem asked for the negative. The problem asked for a negative of that. So I ignored the negative to find the value and then took the negative of it. That's all. Like I said, it wasn't particularly interesting. All right, so we'll talk a little bit more about this next time. In particular, one of the things I want to talk about next time is how the standard normal distribution relates to the chi-squared distribution, because that's going to be important later on. We'll also get into bivariate distributions. So when we have two random variables versus one, doesn't that sound like fun? Okay. All right. Have a good one. Remember, no class on Tuesday because of the advising day. Make sure you make appointments with your advisor to get ready for the fall semester. Pizza at noon on Tuesday. Okay. All right. Have a good one. Anybody want to go to my meeting for me at 12:30? No? No takers? Okay. It's our Arts and Sciences Directors meeting. Issues with the college. Yeah, yep, you too. Nothing interesting. Let's just put it that way.
Is it still 2 to?
That works, yep.
I have a question. I think you didn't get